Which one? This is 142 should be?
Display. Display.
I mean, I have to check this. Right, it's US, right? Sorry. And then I've probably messed this up. This one was 2T. No, thank you. Okay, great. Okay, and we can check this against Brzezinski now. Brzezinski has, I think, equation 6.5.6. I think in the last two lines, the S and T should be interlinked. I think there's a typo there. I mean, I haven't gone to check his website, but maybe I got it. What do you think? Okay, I think now it agrees. So I check the S and T. So T and U should be 1, 3, 2, 4. Okay, and 1, 4, 2, 3. Okay, and the others. Okay, good. So modular that shift set, which I think is a typo, this agrees with it. Okay, so very good. So just to remind you, we were discussing the Venetian amplitude last time. We discussed how we had vertex operators inserted in various different orders. And given a particular order, every particular order is associated with an integral of the sort. Was this 2 correct, by the way? 2 correct. Yeah. Okay. Yeah. Was associated with an integral of this sort. But what went in here, whether it was ST or SU or U, and note also this is symmetric under integration of ST under variable change x to 1 minus x. Okay. So which variables appear? Basically the adjoining momenta with 4 and 1 and 4 and 2. Now, you might wonder what's special about momentum 4. Suppose we look at this diagram and let me do it with treating the momentum 3 as or the momentum 2 as special. You can do that and you get the same answer. Because 2, 4 will be associated with 1, 3, that's T, and 2, 3 will be associated with 1, 4. That's T. See, we chose to have 4 sides equated over, but we could choose to have any of them. Okay, there's another thing that I didn't describe in that much detail, I couldn't have last time, which is, the way blindly using formalism would get this would involve 2 integrals over y4. An integral from minus infinity to infinity, one in which 1, 2, 3 are ordered as left of the board, and left of the board, one in which 1, 2, 3 are ordered as the right. Okay, so we get all these 3 regions, but you might think that they don't look quite like the same integral. One of them is an integral from minus infinity to 0. The other is an integral from 1 to infinity. So how did all those integrals become the same? Well, they had to, of course, because that's the symmetry. But if you want to see it explicitly, you can just use change. You can convince yourself by change of variables that these integrals are the same. Okay? So, for instance, the integral from 1 to infinity will become the integral from 0 to 1 under the variable change x goes to 1 by x. More important variable changes to the dimensions. Okay? So it has to be, but you can explicitly check the readings. Is this clear? Okay? Very good. So I suppose we're happy with this formula, and now we want to understand its physics. Okay, so let's go on. The first thing we want to know is to understand what this AST business is. So AST is very simple. It's a simple thing to understand completely analytically. Once we use this classic formula for beta, the beta of AB, which is by definition equal to gamma of A plus B, gamma of A and gamma of B divided by gamma of A plus B. Okay, is given by the integral formula dy y to the power b minus 1, 1 minus y to the power b. Okay? All of you have seen this formula before. All of you know how to derive it. Well then, it's very easy. One of that next. I'll leave it. Yeah, I'm not getting bothered with it. Okay, so here's the integral that we have of this form. Once we identify A with minus x minus 1 and B with minus t. So, AST is equal to gamma of minus 1 minus s, gamma of minus 1 minus t over gamma of minus 2 minus s minus t. Now remember that s plus t plus u, okay, was equal to minus 4. Okay, so this minus s minus t minus 2 can equally be written as u plus 2. These are various different ways of doing it. Okay. Okay, very good. So, what are we going to do with this formula? So, the first thing we want to understand about this formula is its singularities. Okay? So, the thing that we're going to try to understand is what the singularities are as functional momentum. So, we're going to search, okay, just immediately from the structure of this answer, see it's a product of gamma functions over gamma functions. Okay? Now, gamma functions, the singularities of gamma functions are poles, okay, at 0 negative values of the good of the argument function. Okay, so immediately from the structure of the formula we see what they get poles. Where are we going to get poles? So let's look at the variable s. Where are we going to get poles? We're going to get poles where alright. I thought I would keep that in. Okay, I'm going to delete your field to one of you. Okay. We get poles with minus 1 minus s is equal to negative n. N is equal to 0, 1. Okay? Which means that s is equal to n to minus 1 for non-negative n. Okay. So now we've got two particles colliding. Okay? When you get poles, you get, this is all 3 level structure. You get poles when that collision can produce an intermediate particle. It propagates and gives you the other two particles at the end. Okay? You get poles when you sit on the mass of this particle. Okay? Now, let's form the fact that you can get poles at these values of x tells you what particles can be produced in string theory by colliding with tachyons. They're particles that have masses that have s is equal to n minus 1. Okay? Remember in our conventions we absorbed an alpha prime into s. So if we restore dimensions, s is equal to 1 by alpha prime into minus 1 plus n. So this is m squared of the particles that can be produced. And this is exactly the same as mass formula we had for strings. Okay? The minus 1 giving the tachyon, n equals 1 gives you mass of states, photons, and higher n will give you the mass. Okay? So that's very satisfying. That's the first consistency. The particles that can be produced from the scattering of two tachyons have the same masses as the states that are present in them. Okay, so now let's analyze this thing a little bit. Okay, now understood this, we know that there's only one source for the singularity at, for instance, n equals 0. The intermediate particle must be attacked. Okay? So now we have both a consistency check and an opportunity to clear up some ambiguities. The consistency check follows because we know the 3-point caching of 3 tachyons is being computed at. Okay? So the structure of the singularity must be exactly in the form of two 3-point vertices, okay, times the pole for the tachyon, which we also understand. Okay? And the opportunity we have is that there were some things that we left ambiguous in our calculations. Namely, what factor we put with each vertex as we inserted into the stacking amplitudes, we'll be able to clear that up. As follows. You remember we had a similar discussion during the last semester, which is okay, so first let's study the residue of the singularity in more detail. Okay. So let's look at this object. Let's look at this object and set S is equal to -1. Okay, so S is equal to -1. This guy here becomes -1 -3. Okay, and kills this object. Okay, so we've got gamma of -1 minus S in the limit that S goes to -1. But gamma of x as x goes to 0 is 1 over x plus corrections. Now you see that from the formula that gamma of 1 plus x is equal to x times gamma of x. But we know gamma of 1 plus x in the limit x goes to 0 is 1. So that tells us gamma of x in the limit x goes to 0 is 1 divided by x. Okay? So this thing, to sign is the same thing as S plus 1. Okay, it's 1 over the thing that will go to 0. 1 over the output. Up to some sign. Okay? And times what? Times 1. Because the residue of this code is just 1. These two things. Is this clear? Okay? So, from this term we got 1 over s plus 1, but it's clear if we replace t by u, we get the same thing. Right? So, AST and ASU both have a pole with residue 1 at s equals 1, at s equals -1. Okay? So, the singularity structure in s equals -1 is what? Now you're going to need to help me. I need the yeah, it could be minus. I'm not keeping track of signs. Yeah, there are all sorts of i's also that we draw. Okay, we just understand the structure. Okay, yeah, you're right. Okay, so so now we have to keep track of quotients. So what we get is 1 times all the trace structures that appear in AST and ASU. Okay? Now what are the trace structures that appear in AST and ASU? In AST we have 1, 2, 4, 3 and plus 1, 3, 4, 2. This was from AST. And from ASU we had 1, 2, 3, 4 plus 1, 4, 3. Okay. Now, see these two terms combined together into 1, 2 times anti-commutator of 4 with 3. Okay? And these two terms, now the trace is cyclic. So we can take the 2 down this side in both of these two terms. And these two terms then combine together as 2, 1 times anti-commutator of 4. So the whole answer is trace of anti anti-commutator of lambda 1, lambda 2, anti-commutator of lambda 3, lambda 4 times divided by x plus 1 plus various factors we found. Yeah, numerical factors. Actually, numerical factors are pretty trivial here. But anyway, we found that. Is this clear? Now let's compare this with what we would expect from the stacking of three cations and then cation running in the middle. Stacking two cations give you a cation running in the middle. So, okay, remember that we had computed last class that the three cations carrying amplitude between 1, 2 and 3 was anti-commutator of lambda 1, lambda 2 times lambda 3 is that, and no factors of momentum. Constant. Okay? So what do we expect for the structure of the singularity? What we would expect after numbers which we'll work out in the next one, what we would expect is that tachyons of all colors are. Okay? So we'll have trace of lambda 1, lambda 2 times lambda A times trace of lambda A, lambda 3, lambda 4. Sum overall. Okay? Now lambda A is the is a basis in the space of n cross n matrices. So you choose basis to be having one element 0, non-zero and everything else 0 in all the n squared places. Okay? And now you can easily convince yourself, basically from the observation that over any complete orthogonal basis, n is equal to Rn. Okay? Think of these lambda as the basis in the space of n squared dimensional matrices with some obvious inner product, namely the trace of products of matrices generating the inner product. Okay? You can convince yourself that this is the same thing when we do the sum over as trace of lambda 1, lambda 2, lambda 3. Okay? So this matrix structure that we see up here is beautifully reproduced by summing over all the intermediate colors of the tachyon. The remaining coefficient was 1, and then we expect to see, of course, this divided by the whole, x plus 1. So that's exactly the same. Okay? In full detail, we recover exactly the structure of the singularity that we expect. In full detail, we recover exactly the structure of the singularity that we expect from our knowledge of 3-point amplitude from the form. But now okay, any questions about this? Is this clear? Okay, good. So now that we understand this, we can use it to advantage. So let's try to use it to advantage. Now let's try to be a little more systematic by keeping factors. I still won't keep numbers 1 and 2 by look up, which is okay, but just keeping the important unknown factors. Okay, so the unknown factors are what? You see, every time you insert a tachyon vertex operator, you do so with an unknown with some coefficient. So let's say that's G, we call that GT. Okay? And in addition to everything that we've got, you see, if you remember our rules for computing the correlation function for the worldsheet for this, they were rules for computing correlation functions. So these rules actually gave us the correlation divided by the partition function. So, but in string theory, we need the whole path integral on this for these vertex. So there's a product of the partition function also then the answers. Okay? So for instance, what is the 3-point function of the tachyon proportional to? Apart from the color factors, it's proportional to GT cube times this partition function on the disk. no vertex operators inside the double disk. Okay? Now, as always in field theory, it's very hard to compute these objects. It's much easier to compute ratios of partial insertions. Of course, it's possible, and string theory has been studied so extensively that people have done it very different ways. But, but suppose we were trying to cheat. We didn't want to go through the bother of computing this CD. What did we say about it? Well, you see, this is what the 3-point function was proportional to. So, when we do this analysis more carefully, we get a factor of this thing squared from 2 3-point functions. But from the 4-point function, we get gt to the 4th times c. Remember, it's the same CD because the partition function on the disk is the partition function on the disk. Okay? So that immediately tells us that gt squared is equal times cd is equal to 1. So it relates the unknown normalization in front of the tachyon vertex operator, okay, with the partition function on the disk. Now, this may not seem like much progress yet, but what we find is that by doing the same systematic analysis for every particle, we can find all the GTs, okay, in terms of C. So all ratios of these primarily unknown normalizations of the vertex operators are determined. Okay? The absolute value of the normalization is not determined, and that is nothing determined because string theory has the dilettante field, whose expectation value at infinity is a coupling constant, can take any value. So nothing will determine its absolute value, but all ratios. Is this clear? Okay? So now, I just made this assertion that every other field's normalization is also determined, but from the same amplitude. Okay? And let's check that that's working in detail. Okay, so let's look at the same amplitude and look at the factorization on the. Let's look at this. The same amplitude. We will take the same amplitude and look at the factorization on the massless channel. Then we are x equals 0. Okay. So now let's do that. Okay. First question, comments. Is this clear? Questions, comments? Okay, so now let's take the same amplitude, which is gamma of minus s minus 1, gamma of minus t minus 1, divided by gamma of minus s minus t minus 2. Okay, and look at how it factors on the massless. Okay, so the massless channel is at s equals 0. So when we said s equals 0, what do we get? Well, the first thing is that we get gamma of minus 1 rather than gamma of 0. The gamma of minus 1 is equal to gamma of 0 up to a factor of minus 1. Using the identity that gamma of x plus 1 is equal to x times gamma of x. Okay? Not keeping track of signs again. So we get the same kind of pole, right? So this thing gives us a pole 1. Okay? On the other hand, here's something different. Because instead of having the same factor, both in the numerator and denominator, we get a product of gamma of minus t minus 1 in the numerator and minus t minus 2 in the denominator. Now we once again use our favorite identity, gamma of n plus 1 is n times gamma of n. And that tells us that we have a factor of minus t minus 2. In this. Okay? So we have minus t minus 2 divided by x. Okay. Now, this minus t minus 2 is going to prove useful for what I want to do in a minute to rewrite this minus t minus 2 in an algebraically more convenient way. Okay? So remember that we have S in general, s plus t plus u is equal to minus 4. But s is equal to 0 on this 4. So as far as its residue is concerned, t plus u is equal to minus 4. Okay? Therefore, minus t so let's multiply this by minus and bring the 4 on this side. Minus t minus 2 minus u minus 2 is equal to 0. Okay? And so you can write minus t minus, and therefore minus t minus u is equal to, therefore minus t minus 2 is equal to minus t minus 2 plus u plus 2 over 2, using the fact that u plus 2 is the same as minus u plus 2, which is equal to u minus t. Okay, so just a trivial identity will prove useful in helping us understand some structure. Okay, great. So, what have we concluded? We've concluded that from AST we get u minus t by 2 into what is it? The residue is u minus t by 2 times whatever trace factor. Now the question is, what do we get from ASU? Well, it's clear, the symmetry and the interchange of u and t. So we will have the same thing for ASU. So from ASU we get minus of u minus, so t minus u over 2 times whatever trace factor. Hello? Okay, thank you. Okay. Okay, so the final answer. Hello? I'm a professor, I'm in the middle of a class, I cannot take this call. I am not taking this call. Okay. Okay. So we get right. So now we can understand the trace structure. Okay. So now one thing we have to look up. Okay. So ST had what? We have 1, 2, 3, 4 plus 1, 3, 4, 2. Okay? ASU gives us 1, 2, 3, 4 plus 1, 4, 3. Okay? And we're supposed to put a minus sign to these, as we see. Okay? So the full residue, so what's the full answer? Now let's see. You see, here we have 1, 2, 3, 4 minus, that must be SU is that 1, 2, 3, 4, 1, 4, 3, 2, that's correct. And ST gives us 1, 2, 4, 2. Plus 1, 3, 4. That's right. So this minus this is 1, 2 times anti-commutator of 3 to 4. And what about this minus this? This gives us 2, 1 times anti-commutator of, this gives us 4, anti-commutator of 4 with 3. Then this gives us anti-commutator of 3 with 4. So you see that the whole thing is trace of alpha 1 lambda 2 anti-commutator. Now, this once again matches perfectly with what we expect from the photons. Okay. So let's see. How does that work? You see, firstly, let's deal with the color structure. You remember that we have the color structure of the scattering of two cations which give you a photon involved an anti-cognizant of lambda 1, lambda 2 with lambda 3 in the photon. Okay? So, once again, the structure that we expect color-wise is to multiply this with an anti-cation commutator of lambda 3, lambda 4 and sum over, let's call this lambda A. Sum over lambda A. And once again, using completeness under the inner product generated by the trace on the space matrices, this becomes trace of, this becomes this sum over A. Okay? So the color structure is perfect. Okay, what about the rest? What about the rest? Okay, so remember that we also had in our scattering amplitude of the photons a factor of K23. Okay? That thing is going to get squared. So it's going to give us something about momentum squared. T minus u is about momentum squared. And I'm not going to check it for you, but you can check that it is equal to that K23 factor of square. Okay? And this is the pole. That's what we expected. There's one additional factor lying around. That is, if we weren't dealing with these non-normalized alpha primes, there's an additional factor of alpha prime lying around here, because there's alpha prime T minus alpha. Okay? So now, once again, we can either play this game to relate the normalization constants of the normalization that goes into the photon scattering amplitude to that of the disk. So what do we have? We have a 3-point function as gt the whole thing squared times g photon, then this whole thing squared times cd the whole thing squared. The 4-point function, as we just seen, as gt is equal to the 4 times cd and times some additional factor alpha. Okay? So, now the gt's up to the 4s, they just cancel. So we get gp is equal to, and 1 power cd cancel. gp times cd is equal to 1 over alpha prime. Okay. If you work it out really carefully, with all coefficients and so on, you get that g photon is equal to 1 over, and this is g photon squared. So you get that g photon is equal to 1 over square root of 2 alpha prime times g time. Okay? And the interesting thing is that this is the same relative normalization that follows from the state operator. So let's take a minute to just understand what that last statement that I made, what the last statement that I made means. Okay? So remember that what are we really doing in this training? Well, what are we really doing in this training? We're starting with some open string here and sending it at, starting with some open string, some other open string, some other open string, some other open string. Okay? There's some word sheet which has these long tubes that describe these open strings coming from infinity. And then jolting off like this. And then we use the fact that a long strip like this can be conformably related to a little patch like this with the insertion of an operator, namely the state operator. Okay. To replace this calculation of physical interest, calculation which have these long strips going off to infinity, by the calculation of correlation functions of the corresponding vertex. Now the states that we selected were normalized. Okay? So we don't clearly have any physical ambiguity in what the factors that go behind each vertex compensations. You know, we have to start. We're supposed to start with normalized states and determine the correct vertex operators with normalization that are given to these normalizations. That is an exercise that's not difficult to do, and that either we or you in an exercise did or was supposed to do last time for closed strings. Okay? So this relative normalization can just be obtained in that fashion, just starting from the state operator, starting with normalized states, and then determining what the operator corresponding to that state is. Okay? So that gives you relative normalizations directly. So there are two different ways of getting these relative normalizations. First, sort of from logic, from the state operator. But second, just by taking the answer and saying, if it's describing the quantum field theory, there's unitarity and so on, it must be the these relations as such. And these two ways give you the same answer. Okay. Finally, this relationship that I haven't written down the numbers, but that's C beta and GT the whole thing squared into 1, or 1 over 2 pi, whatever the right answer is. This can also be verified with a careful calculation of C with careful normalizing, keeping track of normalizations. Okay? When you define things correctly. I won't go into that. So, what I want to say is that every element that we've used by assuming unitarity, and assuming that we get the same structure of singularities as dictated, you say, the way I presented it, and I said that if you have a quantum field theory with exchange of particles like this is what you're going to got. But that, doesn't require you really to have a quantum field theory. Because in the end, the structure of singularities, being determined by lower order graphs, follows directly from unitarity. Quantum field theory has in it inbuilt the structure of unitarity, so it's a convenient way to analyze these things by referring to our previous normative quantum field theory. So what we're really doing is using unitarity. We're not using the ideas of quantum field theory at all, except for as a mnemonic. Okay? So what we've been doing the last 10 or 15 minutes is A, checking that the structure of the amplitudes is consistent with unitarity, and B, fixing some normalizations to ensure the unitarity bang on. But all these normalizations could have been obtained by other means as well, so it's a check. Okay? Also, of course, the structure is there. Right? So, for instance, the fact that we have this T minus U here was necessary for unitarity. If we just got 1 in the residue of the photon amplitude, that would not have been consistent with unitarity no matter what constants we choose. It has to be the product of the 3-point amplitude squared divided by the pole up to some number. So that's stringent taken in both. Is this clear? Okay. So the last thing I want to say about this, the last two things I want to say about this Venetian amplitude is, firstly, let's look at it again. So you have gamma of minus s minus 2, gamma of 1, gamma minus t 1, gamma of minus s minus t 2. Okay. Now you remember that we have suppose that every value of s being an integer. Now suppose we have a pole that s is equal to a. What is the kind of residue we're going to get? But if we have a pole that s equals n, then this gamma function is gamma of minus t minus 2 minus n plus n. Well, this gamma function is gamma of minus t minus 1. Minus 1. So that's n plus 1 integers separating this guy from this guy. This guy is larger. This is an additional negative number. So we're going to get the factor t minus minus 2 into minus t minus 3 all the way up to minus t minus 2 minus n is the residue of this. Okay? Now suppose we take all energies to be very large. So the t is very large. Roughly speaking, this is about t to the power n. telling us that though we haven't computed it, the scattering of two tachyons to some state at mass level n, that amplitude must have n plus 1 powers of the momentum. So that thing is going to be us. Okay? So what's going on here is quite interesting. You see, the tachyon can produce all the particles that it produces. And the coupling with the tachyon to these increasing high mass particles grows at like increasing powers of energy. Now you might think, wow, this is a recipe for disaster. We take the energy, we go to very high energies, and amplitude is going to blow up really badly. Because, well, the amplitude to produce a mass 0 particle already is high, amplitude to produce a mass 1 particle higher, and so on, it's just blowing up. But that is not the case. That is not the case. We can directly see from an axis of the amplitude. Okay? So, for instance, if we take S to be large and T to be large, but keeping the ratio of S and T finite, okay, what does this answer become? Okay, if we take S to be large and T to be large, keeping the ratio of S and T finite, this answer becomes exponentially suppressed in e to the power minus S and e to the power minus T, as we have seen last time. For closed shapes. Everyone remember this? Should we quickly go through this again? It's just using the fact that the formula that gamma of n is sort of like n to the n times e to the power n plus something. Okay? Using that formula and cancelling all things that cancel, okay, you'll find exponential suppression. So, okay, that's not good. You find exponential suppression at large energies. As we worked out for closed strings, same business. Okay? So, it's not true that amplitudes are going on at high energies. Even though things are coupling to any individual particle, like a higher and higher power of energy. Okay? That's the miracle of string theory. You've got all these other particles living. And if you isolate the contribution due to one particle running in an intermediate atom, it looks like it's becoming very dangerous. However, if you sum it all up, what you're seeing is that what's propagating in the middle is a soft, puffy string, which has size, a large form factor, and therefore amplitudes are exponentially suppressed. Okay? So that's the beauty of this formula, that although individual things coupled with high momentum, the full answer dies off very rapidly. Okay? It's the softness of string theory that we see before this. Visible again in this formula. That is the lies at the heart of this ultraviolet, it's good ultraviolet properties. Okay. Any questions about this? Okay. By the way, this one obvious comment, so if you look at the photon, you see from this structure that have you been dealing with the U1 theory, there is no amplitude, there is no singularity at S0. Because strong has vanished. That of course is consistent with the fact that the photon is uncharged, that the tachyon is uncharged under the photon in the ability. Okay, good. Any other questions or comments? Otherwise, I think I'm going to stop my discussion of tree and amplitudes. Yeah, body weight. Okay, so now in today's what's left of today's class, which is not much given that we are all eager to go to the asset, but okay. In what's left of today's class and in Wednesday's class, what we're going to do is to discuss loop amplitudes. Now, I couldn't remember last semester how much did we talk about loop amplitudes in the question. Did we discuss one loop amplitudes? I couldn't remember doing it. No. Nobody remembers it, so we probably doesn't follow it. We probably didn't. Okay, so I'll start with a brief discussion of loop amplitudes for the closed string, and then move on to the discussion of the loop amplitudes for the open string. moduli, measure moduli space for the torus. But I can't remember actually computing anything. So let's go ahead and do it. Okay. So set, just to set the stage and to remind you again, I'll derive our computation of measure of moduli space on the torus. Okay. So recall. Recall that according to our the general structure of string theory, every modulus appears with a B insertion. Okay? And the B insertion was the integral of square root G times B alpha beta, G alpha theta, G beta phi times del by del T of G theta. Sorry, there? Can you show me this? Yeah, you see, I think we just talked about the major moduli space. We didn't, so I think we can tell you some things about the actual we didn't try to compute the vacuum energy of the string. Did we? But did we put in the torus function as well? Oh, we did, huh? Yeah. Okay. Yeah, we did. So we discussed Luga. It's quite shaped as a fact, remember? Okay, so let me give you just in the remaining 15 minutes a quick reminder. I didn't remember, none of you did. It's clearly not fresh in you. Okay, so very quick reminder. Basically, I'm going through this reminder because most of the gymnastics we do here will be very similar to the gymnastics we do for questions. Okay, so in a more familiar context, I'll remind you what we did, and then move on to the discussion. Okay, yes. So first thing about the integral modulus. Does everyone remember that every factor of a modulus, the modulus in this case is t, okay, appears with such a factor. This you remember, right? The basic factoring amplitude formula. Okay, we're definitely going to have an exam in this course. So when we finish our discussion of T duality and so on, basically, and maybe in a month, we will finish a discussion of everything in volume 1 of Collisions. Okay? Then we're going to have an exam of everything in volume 1 of Collisions. Okay? Okay? And I expect you all to do brilliantly in this. Okay. Right. So, according to the general rules we developed, for every fact, you remember every modulus had a B insertion. But it's not enough to say B insertion, to say what B insertion. Then this was the B insertion. T was the modulus, we got the B. Okay. Now, you remember that we parameterized our tori by this modular parameter tau. So torus was a space with metric dz, dz bar. And with identification z is equal to z plus 2 pi and z is equal to z plus tau. Maybe we call it 2 pi. Okay? Now, this is, from the point of view of this formula, this was a strange way of parameterizing the modulus of the torus, because we changed the domain over which things were made, the space was located in, rather than changing the metric. But you also remember that, as we discussed last time, by a change of coordinates, we can undo that. So suppose we have two tori, one which has modular parameter tau, and the second one which is modular parameter tau plus delta. Okay? Then we want to look at what tau plus delta tau, what space this is, keeping the coordinate identifications the same as they were when the modular parameter was tau. So we make a variable change to make the variables have the same identifications. Z equals to z plus 2 pi, z equals to z plus tau. Okay? But that will change the metrics. We want to see what the metric, what the change to the metric was. Okay? So how do we do that? So we've got some new W coordinate. So let's suppose that we have the coordinate Z, which have these identifications. Z is equal to Z plus 2 pi, and Z is equal to Z plus 2 pi tau plus delta. And now we have some new W coordinate which has identification. W is equal to W plus tau 2 pi, and W is equal to W plus 2 pi. We're going to variable change the goes between these two. So we suggest that Z is equal to, and in this space, the metric is dz dz1. Okay? We have Z is equal to AW plus BW bar. Okay? And we want to determine A and B. So we have two equations to determine. Firstly, if we put Z is equal to 2 pi, that should be consistent with W equals 2 pi. So we get A plus B is equal to 1 from that formula. And secondly, if we put Z is equal to tau plus delta tau into 2 pi, that should be consistent with W is tau into 2 pi. So this identification point should be the same on both cases. Okay? So 2 pi cancel out. So we get A into tau plus B into tau bar is equal to tau plus delta tau. This is clear? Anthony, you're looking puzzled? No. So, see, what we've got in a space with metric dz dz bar, and whose identifications are z is equal to z plus 1. Let's get 2 pi, let's call it 2 pi. So that's easier to speak. Z is equal to z plus 1 and z is equal to z plus 2. Okay? Now we've got two different spaces, one with tau and one with tau plus delta. So, you know, I had thought of as patches of the plane. These are different patches. Okay. Now, this is a fine way of characterizing the vector, right? However, in this formula here, what we're assuming is that we work with spaces on the same coordinate range, but have different metrics. What we did initially is choose the same metric on both spaces. I mean, flat metric, but change the coordinate range. Now, these two things are equal upper coordinate range. Okay? And I'm trying to find the coordinate transformation that makes them manifest. So how do I do this? I have these two different tori, one with tau and one with tau plus delta. What I want to do is to make a coordinate change that will pull this identification together in the new coordinate. The new coordinate is called W. Okay? So what I mean is that when I say W equals tau, I get Z is equal to tau plus delta. So I'm guessing that the coordinate change is linear. Z is equal to AW plus BW bar, and I'm going to try to find that linear coordinate change. Okay? So I have two unknowns that I have to determine A and B. I need two equations. So the first equation is that one is the same in both coordinates. And the second equation is that tau in the W coordinates is tau plus delta tau into Z. So that's the first equation. I said 1, 1, 1. Second equation, tau plus delta tau, A tau B tau. Okay? Okay. So, I'm not going to get too far. Negation. So, but clearly, since nobody remembers this, it's worth going through it. Once again, so. Okay. Yeah. It's tempting to just skip to the open strings. We have to. But yeah. So, very good. Now let's solve. Okay? Tau is solved. Let's multiply this equation by tau and subtract. Okay, so we get B tau bar minus tau is equal to tau tau cancels delta. So B is equal to delta tau over tau bar minus tau. Okay, and now also multiply this equation by tau bar and subtract. So we get A into tau minus tau bar is equal to tau minus tau bar plus delta tau. A is equal to 1 plus delta tau over tau minus tau. important change that we had to do was z is equal to w plus, and then there is one by tau minus tau bar, the delta tau over xw plus delta minus delta tau here is the w. Okay? So the metric which was dz bar in z space becomes something in w space. We don't know what that something is to first call in delta tau so that we can differentiate. But also we don't care about all components. We only care about those components that will have non-zero overlap with B. And remember that B was purely holomorphic or purely antibody. There's only a BZZ component or a BZZ bar component, no B's component. Okay? So, what we're going to get from this, since the ambient space is just eta, okay, is BZZ times del GZZ, Z bar by the modulus under consideration, del tau alpha, plus BZZ Z bar times del GZZ and del tau. That will be one term we want to compute. And then the second term we want to compute by tau is replaced by tau. Those are the two modules. Okay? Plus second term with tau. Okay? So we need to know how GZZ bar and GZZ vary is a function of tau. Okay? So we need to compute the omega. Okay. So we need to compute the part that has dw squared and dw bar squared to first order tau and delta tau. So the part that has dw squared clearly has one term from here, the dw, but it gets the second term from dz bar. So from here, minus dw times delta tau bar over tau bar minus tau. Okay? And then the part that was dw bar clearly gets one term from here, dw bar. The second term is dw, so that's this, minus squared delta tau over tau minus tau. So what have I done? I've taken dz bar. I've taken the metric dz bar and written it in terms of w coordinates, not keeping two first order and delta tau, not keeping track of the dw bar part that I located. Okay? So we conclude that dgww by d tau is 0, but dgww by d tau bar is equal to minus 1 by tau bar minus tau. And similarly, dgw bar w bar by d tau bar is equal to 0. Include that by looking at this. But dgww by d tau is equal to whatever we get from here. Now minus 1 over tau minus tau bar. This is clear. Okay? So, then using that formula with the formula gone, this one, we find that the two insertions that we need, are, this one is non-zero, so we get B times z bar, B times minus 1 by B times tau minus tau bar And we have a second insertion, which is b bar times right now bar. Okay, so these are the two insertions that we have to do into our math. Is that clear? Okay, so this we can write as b times b bar times in tau the whole thing squared times factor. And we need to just figure out the factors. Factor here is 1/4. Like some I, okay, forget about the factors. You do that. Let's focus on the important ones. Okay, so this is what we have inside our insertion. Okay, now remember what we did with the C insertion. You remember that, oh, I should have reminded you about this in the beginning, that the torus had two conformal-King vectors, namely the vectors which are just the constants, and two moduli, the moduli using explicitly, the types. Okay? So we dealt with the insertions that come from the two moduli, but we haven't dealt with the insertions that come from two conformal-King vectors. Okay. Now, however, these two conformal-King vectors are one analytic and one anti-analytic. So we can deal with that, those two conformal-King vectors, by fixing one vertex operator. Like the analytic and anti-analytic position of the vertex operator. Okay. However, so what we would get then is C of Z, C bar of Z bar, times the vertex operator at Z and Z bar. Now we use two facts. The first fact is that this C operator, as you know, the insertions of these operators pick out only the zero mode. Right? Because the integral of the zero mode will otherwise have to be zero. And the zero modes in this case are just constants. Okay? So these C operators can, since you're going to pick out the constant anyway, it doesn't matter where you insert. So though where C is inserted is linked to where the vertex operator is inserted in logic, on the torus we can move C and C bar insertion to any point. Because everywhere you can pick out just a zero mode. What you get is value of the zero mode evaluator at that point. The value of the zero mode is the same thing at every point. Okay? So, okay, yeah. I'm sorry. Here I omitted the D to Z. Here I omitted D to Z as well. So this will be the ability to Z. Okay, it's 2 minutes more. Let's finish this. Okay. So the first thing I do is I move these C's. Okay, I move these C's both to the origin. I can do that, right? I can do that. Move that ahead. Then I take this vertex operator. The initial insertion of the vertex operator can be done at any point. So instead of inserting the vertex operator at a given point, we could have the vertex operator inserted at point Z1 and integrate D to Z1 divided by the integral of D to Z. Normally that would be quite complicated because the insertion position of the C operator is linked to where you insert your vertex operator. But on the fact that the torus, for the reason we mentioned, you can in every case move C to the origin. Okay? What's that saying? That's saying that you can convert the fixed vertex operator once you put two insertions of C at the origin. You can convert the fixed vertex operator to an integrated vertex. One, if you also pay the price of dividing through by the volume of the torus. Okay? So now let's put everything we said together. So, as far as the torus is concerned, what do we get? We got, and remember also that B is a constant. So these integrals are trivial. So we can think of this integral over B as B is 0 times volume of torus. So what is full insertion? Because B is 0, B bar of 0, C of 0, C bar of 0. We get this piece. Then we get a factor of 1 by in tau, the whole thing squared, from these explicit factors we got. Times we get a factor of 2 powers of the volume of the torus. That's this V2 Z. Done the integral replaced by V of 0 times. Okay? So the volume of the torus is even tau of the volume. Times, we have to divide by one factor of the volume of the torus due to this trick of converting the vertex operator into an integrated vertex operator. So we get the digital factor of 1 by E tau from that. Okay? So this is cancelled this, and the next result is d tau by E tau. And times C of 0, C of 0 bar, C bar 0, B of 0, B bar 0. And now, after this, all vertex operators have to be treated as an integration. This is now very symmetrical. Is it clear? Okay? Now, although we went through this derivation, by fixing an operator and then unfixing it, just because we wanted to use the general results we had, the key point here was that the 2 conformal field vectors that we had left unfixed, we didn't need to fix anything, because the remaining symmetry that was left unfixed was just the volume of the torus. Integrating over the coordinate changes that generated the unfixed gauge symmetry just gave us the volume of the torus. So instead of fixing those unfixed gauge symmetries, you could have just done the integral terms. We get a finite volume. Okay? And dealt with so for the special case of the torus, we could have thought of gauge fixing in a different way than fixing a particular vertex operator. Okay? And we could have got this answer directly if we did smart enough from the beginning. The only point I want to emphasize is that this answer is correct even when there are no vertex operators. Even though in our derivation we need to have a vertex operator which we fix and then unfix and so on, the final answer is correct even when we don't have vertex operator. I'm not going to try to derive this for you, but if anyone's uncomfortable, we could have a little session on doing it. Okay? So, this is our final answer for all amplitudes of the torus, including the vacuum amplitude. It's the vacuum amplitude, there was no vertex operator to fix the conformal gradient. Unfixed. But that didn't matter, it was finite. We really need to fix it. Okay? So this final answer is correct for everything, including vacuum amplitude. And I'm going to treat this as a starting point of our analysis of the vacuum amplitude in 10 or 15 minutes, because we've done this before. Next class, before going on to discuss open strings. Open string amplitude. Okay, so let's break now. We'll go for the asset colloquium. But there's an exercise I want to suggest to you guys. Try to derive try to follow what we just did for the torus, to do it instead now for the cylinder. Okay, the shape that will be useful for 1-2 amplitudes for open strings, and see if you can derive the correct measure factor. For getting an analog of this formula for amplitudes. We'll do it in class next time. It would be good if you try to do it.